We'd like to start off by talking about the final exam, and I do actually have some exams to return to you here, and we'll do that at the end of the hour. Final exam review sessions, these are review sessions that are open to everyone. I have put this out here on D2L for 10, 10, 20. Those times here are today at 10 o'clock. And then we do have a review session available on Friday at 11 as well. And these are down in the Academic Support Center. There will be a review packet that they pass out there. They'll go through questions, whatever else. Students from all sections are invited to this. So you may see some students that are in there that are not a part of this class. They could be from one of my college class. They could be from my online class. So everybody's been invited to these. These are not directed by me, but they are rather directed by our Academic Support Center staff. The final exam in here itself. Here are the details we need to know. And I need to actually look this up. So let's go ahead and do that. This is in our syllabus. And I'm looking for the schedule here. There we go. Looks like we have our final exam scheduled for Thursday, December 15th at 7:30 a.m. It's scheduled for a 2-hour block, and it'll be in this room. So again, Thursday, December 15th. Time is 7:30 to 9:30 a.m. And that'll be in this room here, S235. As far as what to expect on the final exam itself is worth 200 points. And this was in your syllabus on day one. What material does the final exam cover? Everything, exactly. This is a cumulative exam, which means that it covers everything in here from day one. It could cover stuff that we covered in lecture, stuff that we covered in lab. It could cover stuff that's been in our reading that we've not covered in lecture. But the definite focus is going to be whatever we've covered here in lecture and whatever you've seen show up on the previous exams. Now, because each exam we can't test you on every possible thing, it is possible that something could show up on the final exam that you were not tested on previously. For example, on this last exam, you had a molarity problem. I could not put every single possible combination of molarity problems on there. I think that on this last one, you were asked to calculate a mass of sodium carbonate or sodium bicarbonate, something like that. So on the final exam, you might be asked to calculate the molarity or to calculate a volume. But it's still the same type of thing. You're still going to use the molarity relationships and random mole relationships to arrive at some sort of answer. So just like on any other exam, it's impossible to test every possible combination. Same is going to be even more true in the final. It's impossible to test every possible combination. Which means you need to pretty much practice things that you are least familiar with or things that you have done the poorest on. If there's something that you know very well, for example, nomenclature, I wouldn't spend a whole lot of time with nomenclature. But if you struggle with gas laws, then I would certainly spend more time studying gas laws. We have 13 chapters, is my recollection, that we've covered altogether. So there's plenty of materials that need to be covered on this exam. One thing I see that I missed here, there's going to be 50 questions on this exam, and all of the questions are going to be multiple choice. Now, don't go ahead and celebrate because it's multiple choice, because I know some of you do struggle with multiple choice, and you think it means that there won't be any problems on there. There will be. The difference is that any calculation type problems that you have will have potential answers that may be arrived at. So, for example, if it's possible to do a calculation incorrectly, it's very likely that you will see possible incorrect answers there or choices. And by possible incorrect, it means ones that are very common calculation errors that are found in the various questions. Because there's 50 questions and it's worth 200 points, that means that each question is worth 4 points each. And I know for some it's 4 points, that's a lot, but it's all relative in the grand scheme of things. If we had 100 questions, they would be worth 2 points each. But chances are you're going to get twice as many wrong. So that's just the way the law of probabilities work. So by having 50 questions on there, that should give you more time with each question to arrive at the possible results. Any questions you have here on expectations? All right, now when you came in, there was a question waiting for you on the Socrative app. How many of you answered that question already? All right, great. We'll see how we did on that question. All right. Looks like it's 100% unanimous decision. So those of you that did not take the time to vote and hear your colleagues decided for you, that you can use your note card on this exam. So those of you that did not vote, sorry to step in. I hope I am not disappointing you by the rest of your peers in this exam voted. Anybody that does not have a note card, raise your hand. Okay, at a minimum, on this note card, you need to have your name. Okay, so you need to have your name on there somewhere. Outside of your name, whatever you put on there is up to you. You can put on, for example, if you had issues with your polyatomic ions, you can put your polyatomic ions on there. If you had issues with how to balance equations, you could put some examples of balanced chemical equations. If you have a couple of definitions, you can put down definitions. Yes. You use both sides. So the primary requirement of this note card is that it's going to be in your own writing or typing. And by in your own, that means that everybody here will have a unique card. I've been asked before, can we run it through a printer? 4-point font. That's fine. Run it through a printer with 4-point font. Just remember, whatever you print out, it's going to be in your own printing, your own typing, or whatever, and your card is still going to be unique compared to somebody else's. The whole idea of that is to get every person in there to study. Okay? And if somebody does one work and somebody does something else and put it all together on a printer and print it out, everybody has the same card and not everybody's done the same amount of studying. So you can type it, print it, write it, whatever. You can use both sides. The other limitation is that you can just do the two sides. You can't put anything onto it or whatever like that. And well, just write on the two surfaces that are provided there for you. And you will be turning this in with your final exam. So when you do it next week, even if you choose not to write anything on it, you still must submit something. The card that you got today, and if somebody's missing today, let them know, because you can't use anybody else's card. You need to use my card and turn that in with your exam. So any questions on that? Okay, I might as well pass back exams here. People that were in lab yesterday got these already, and I should know where pretty much everyone is, but if I call your names, I would like to go over. Connor, Eddie, Anastasia, Allie, Maria, Taylor, Molly, Brian, Shula, Right. Thing to remember here on the exams for the semester, there were 4 one-hour exams. Each one of those exams was worth 100 points. The grade book, I believe I've already updated it. If I haven't, I will update it after class. But if I have updated it correctly, it should show that your lowest exam score has been dropped. Is it showing that right now? Okay. So your lowest one-hour exam score is dropped. The final exam is not a droppable score. So because it's worth 200 points, that means it counts the equivalent of 2 exams. There's a lot of potential in here to improve your grade. Of course, there's a lot of potential in here to destroy your grade as well. But in your favor, what I would say is that historically, the final exam, on average, has been either the highest average exams for the semester or the second highest. And since we all did really well on the third exam that was in here, I'm guessing this will probably be the second highest one. But if you can beat the third exam, that'd be great. I mean, kudos to you. That would be great if you could, but we did all super fabulous on exam 3 in here. Now, because there's 50 questions on this exam, that means, and we've done 13 chapters, that means there's about 4 questions per chapter. So there's not a whole lot. So when you think of each chapter, think about the 4 most important concepts. And those are likely the ones that you are going to see on there. So it's not going to be the most obscure things in there, but the things that we spent the most time with is what you're most likely to see as far as concepts go. There may be some chapters that are more emphasized than others. One chapter I can think of that probably has a little additional emphasis is on nomenclature. If you can't leave a chemistry course and be able to write chemical formulas and write out names, that's a problem. So if you are going to spend time with anything, more than anything else, especially if you struggled with it, I would go back and work on your chemical nomenclature in practicing for the exam. So with that, are there any questions that you have as to what to expect on the final? Okay, grade flexibility in the course. There is none. Okay, you saw the syllabus in here on day 1. So whatever that syllabus says as far as how you earn a grade is how you're going to be graded in this course. I think perhaps if I count up the labs, 1, 2, 3, 4, 5, 6, 7, 8, 13, 14, you are supposed to have your lowest lab score drop. So it's only 140 points, but if you drop the lowest one, that brings that down to 130. So there's going to be 710 points in here total. But again, whatever you earn for a grade is what you will get. No better, no worse. I don't care if you're the nicest person in the whole wide world. If you earn a D, you earn a D, and that's it. So that's not being mean. That's just following up to what I promised I would deliver in this course and what you need to live up to as a part of this course. So any questions on the grades in the course? All right, then we are going to move on. We have chapter 14 left to cover. Chapter 14 is on acids and bases. And I did not get a chance to check out this audio yet. So we will see if this works. Oh, it does. That's kind of pathetic. Guys are like the deadest class I've ever had in my career, but that's okay. It's been fun. So, but let's talk about what happened here. What is it? It's a flask, sure. Now, how about the colors? Very good observation. Why do you think we observed the colors we did? Anybody do the extra credit lab? All right. And what did you observe in the extra credit lab? Yeah, you saw some blue colors, but blue wasn't the only one you saw, was it? Right. And what were you doing to observe the different colors? Okay. And if you added ammonia to it, do you remember the color you saw with the ammonia? And if you added some vinegar to it? Right. And so we get some different colors, and if you look at your ammonia and your vinegar, do you remember how you classify them, acid or base? Vinegar. Well, we can think about this. If you think of vinegar, acid or base, everyone? It's an acid, sure. And ammonia then is its opposite, which is a base. Now, I didn't use ammonia and vinegar up here, but I did use some acid-base chemistry, and that acid-base chemistry what gives us the various colors. Now, if I come back to my kit here that I used for this, and we look at these bottles, trying to say, oh, this is an orange indicator, this is a red indicator, this is a purple indicator. But to get those different colors, I actually used 3 different substances. And one of the things that all these substances share in common is that they color in basic solution, and they're colorless in acidic and neutral solution. So again, something that they all shared in common was that they had coloring bases to them, and they were colorless and acidic. So what I was able to tell, and then there were two different indicators. They were one that's kind of a bluish color, one that was kind of reddish color, and one that was yellow. And then we get my green and the orange and the violet ones, and then mix together different portions of those red and yellow and blues to get the other three colors. So every time then that you saw something that had color in it, that meant we had too much base. And every time we see something colorless, that means we had too much acid. So when we first started, we had these things sitting out here in a row in the beakers. One of the things that maybe you weren't able to see in here is that there's a small amount of liquid in each one to begin with. There's already an indicator in there. And because all of them were colorless, that means that all of them to begin with were acidic. Then I made a round and added this stuff, which is some base. It still remained colorless that first pass through, and that's because I did not add enough of the base. So I made a second pass through. We got an excess of this stuff, which meant now we saw colors, so all of them would have been basic. I then went through with this stuff here to take the colors away, which means that this stuff is an acid. I brought the colors back with this stuff, which means this is a base, and I poured them into here. This already had some liquid in it, which meant that the stuff that was in here must have been an acid. So whenever you go, I don't know if you've ever gone and seen a magic show anywhere, but if you see anything with color changes, what they're really doing is chemistry. It might be acid-based chemistry, but if you're looking at color changes, it's usually nothing more than some acid-based chemistry. But definitely chemistry is what it is, usually acid-based chemistry, because very simply by either manipulating whether it's an excess of acid or an excess of base, I can either get color, no color, or in the case of the cabbage juice, like Anna did with the extra credit lab, you could see some different colors. So there never was a colorless one with that, though, was there? Right. And so took extracted the juice out of some red cabbage, and then by mixing together different combinations of acid bases to get the whole range and colors of acid or base that are present. So with that in mind, now any questions on this demo? Okay, with this in mind, we're going to look at some properties of acids and bases. And some very simple properties of acids and bases would be this. First of all, we're going to make them a table there and break them into the two sides. We're going to compare and contrast those properties. We should mention, first of all, where the word acid comes from. And if you were to taste something that is acidic, like vinegar, how would you describe that taste? Sweet, sour, bitter, what is it? Come on now, vinegar. How would you describe it? Bitter? I wouldn't describe it as bitter. I would describe it as sour. If you taste a lemon, how would you describe a lemon? Sour. Okay, and that's because the word acidus comes, well, it's a Latin word, acidus, and that stands for sour. So if we talk about acids, those are things that have a sour taste. And we actually contrast that with bases, which are things like coffee. Have you ever tasted unsweetened chocolate or cocoa? Yeah, and how does that taste? That is what you describe as a bitter taste. Okay, but now, we don't run around tasting chemicals, because certainly we can taste foods, but if we want to describe things like sulfuric acid or sodium hydroxide, which is commonly known as lye, we can't very well go to the cabinet and be drinking our chemicals to taste them. So what we do then is we use acid-based indicators like we did here to help tell us whether a substance is an acid or a base. So we say that each one of these here change the colors of acid-base indicators. The word base itself, we should mention some other terms that are associated with acids and bases. Sometimes we refer to acids as corrosives, whereas over here on the basic side, we often refer to these as alkalis or alkaline. Sometimes we refer to them as caustics. And where have you maybe heard the word alkali or alkaline before? In the periodic table, but in everyday life. You've heard of the term alkaline or alkali. Battery, sure. Turns out that the long life batteries that we have, the alkaline batteries, are called that because they contain a very strong base inside of them. And if you kept them around for a while and used them, you might notice sometimes that the battery itself may start leaking, and the stuff that comes out, if you feel it, it's kind of crusty and whatever else. You get it on your skin. If it's damp or whatever, you might feel that your skin feels a little slippery. That's because one of the characteristics of bases is that they're used to make soaps. So if you were to get a base on your skin, you say that these feel slippery on the skin. Now, we did not do the soap lab here this semester simply because we have the fall semester is a little bit shorter. But the base that we use here today, this is sodium hydroxide. Sodium hydroxide is commonly known as lye, and lye is often used in drain cleaners. One of the reasons why it's used in drain cleaners is that there's two main reasons for clogs of drains. Now, what's one main reason for clogging drains? Anybody know? One main cause? Something that I'm drawing here. Yeah. All of you are. But what happens is that the air that will get down the drain and will clog it up. Second primary cause of clogged drains usually happens in the kitchen. And it goes up those weeds. Okay? And that's because, as we learned previously, if you have something that's non-polar, like oils and fats, whatever else, and something that's polar like water, water and grease do not mix. Okay? And that's because water is polar, oils, greases, fats, whatever, are non-polar. They don't dissolve in each other. But it turns out that when you use some sodium hydroxide, which is a base, or lye, in the long history, it doesn't matter what our ethnicity is here. Our ancestors used to make their own soap. The way that they make their own soap is they would combine lye with some fat or some oil. And if you mix them up together, then you wind up swallowing soap. So if you get it on your skin, what will happen is that your skin will feel slippery because your skin is full of fat. Your skin is full of fat. And so when it gets on your skin and it will feel slippery, it is actually taking your skin, burning it into soap. Over here, we say that these will react with many metals. They react with several metals to produce hydrogen gas. And another characteristic of acids over here is that these react with carbonates and bicarbonates. To produce CO2. So these are some common properties of these acids and these bases. And one characteristic that they all share in common is that they can cause skin burns when concentrated. So again, they can all cause skin burns when concentrated. So next thing we're going to, first of all, any questions on these? Okay, next up then, what we're going to look at is we're going to look at something we did very early on in the course here. And I believe this might have even been something from day one in the course. And this is going to be your next question on the Socrative app. And we'll see what you remember from day one in here. But the next question here is, does water conduct electricity? So I've brought some stuff over here to test this out in a number of beakers. And I'm going to go ahead and move this aside, give you a chance to get logged in. And so our first question here is, does water conduct electricity? So just look at this if you need to. See what you remember. Day one. Now we can send it in. Just remember me as to how this apparatus works. What we have is a light bulb here, and we have a couple prongs that we are going to drop down into some solution. And if we complete the circuit, the light bulb is going to go on. So we're going to put some water here into this beaker. And we want to test to see whether or not this conducts electricity. So we'll check out to see how we did. We have 57% saying yes, 43% saying no. And we see that water does not conduct electricity. And water does not conduct electricity. Does anybody remember, kind of in general, what we had to do to make water conduct electricity? We had to make it impure, exactly. We had to make it impure. So that's what we're going to do next. So we're going to take another one of these, and we're going to just make sure that neither one of these conduct electricity. So we see that this one doesn't, and this one doesn't. And to make it impure, we add something called an electrolyte. So let's see, I need to go on to another page here. So we are going to be looking at here what we call electrolytes. And these are substances. An electrolyte, let's make it singular. An electrolyte is a substance that conducts electricity when dissolved in water. It's a substance that conducts electricity when dissolved in water. And the two substances I am going to try here are going to be some sugar and some salt. So let's go ahead to the next question, which reads, which substance conducts electricity when dissolved in water? Which substance conducts electricity when dissolved in water? You think that the sugar will, and the salt will, both of them will, or neither of them will? This is the day one demo. Get your answers locked in. We'll count down. 5, 4, 3, 2, 1. All right, and I guess rather than revealing the answers, we'll go ahead and try them out. So we're going to have salt here on your left, and we are going to have sugar here on your right. Get that in here. There we go. We'll go ahead and try the salt. We'll see that the salt is an electrolyte. And we check out the sugar, and we see that sugar is not an electrolyte. So let's see here how we did. Okay, well, majority seem to go with it here. But again, as we observed, we see that sodium chloride is the only one that is an electrolyte. So here's what we're going to do. We're going to make a table. We're not just going to limit it now to the three that we looked at. We're going to look at several different substances. And in this table, what we're going to do is we're going to list the substance in the first column. Then we will give its chemical formula. And then we will ask ourselves, is it an electrolyte or non-electrolyte? Electrolyte or non-electrolyte? And I'll slide that over in just a bit. And so we go down from here. We'll list the ones that we looked at already. First one was water. Formula for water is H2O. And did this conduct electricity? No. So we would say it is a non-electrolyte. Then we went to salt. Formula for salt is NaCl. And we saw that it is. So we'd say that it is an electrolyte. And the next substance was sugar. Chemical. Now this is sucrose sugar. There's several different types of sugar. This one has 12 carbons. Anybody know it from here? C12, H22, O11. You're doing the 6, the C6H12O6. That is not sucrose. That is glucose. We saw that sugar is a non-electrolyte. Well, then we are going to look at a few more here. And I believe these are coming up on the Socrative app. We are going to be looking at potassium nitrate, copper 2 sulfate, and ethanol. So again, potassium nitrate. Copper 2 sulfate, and ethanol. Great practice for writing formulas for our final exam. So as far as formulas go, let's try potassium nitrate. Potassium is K with a charge of how much? It is in group 1A, so its charge is going to be 1 plus. Nitrate is NO3 with a charge of 1 negative. You guys need to review. Alright, so the formula is going to be KNO3. We go to the next one, copper 2 sulfate. Copper 2 means we have Cu with a charge of 2 plus. Sulfate is SO4 with a charge of 2 negative. We have a 2 positive, 2 negative. What happens? They balance. They cancel each other out and we get Cu, SO4. And then ethanol. It's an organic compound now. How many carbons are in here? 2. OL suffix, which means it is an alcohol. Alcohol has CH3, CH2, followed by OH. So these are the three we're going to look at. So we want to know now, do we predict that these are electrolytes or non-electrolytes? And so if we go back to the Socrative app question, which of the following substances are classified as electrolytes? If there's more than one answer, you may select more than one. So select all of the applicable answers. I'll give you about 30 seconds here. Talk with the neighbor if you need to. Which ones would you predict? And while you're predicting those, I'm going to get them out. We will do them in the order from left to right. Get your answers locked in. And we're going to count down. 5, 4, 3, 2, 1. We'll see what our predictions are. Okay. And now I did not put down the right answers because we're going to observe what they are. So we'll start here with the potassium nitrate. I'll first check the water by itself. We see if the water by itself does not conduct. We'll take some of the potassium nitrate and then we'll put it in there. Mix it up to dissolve. And we see that it is an electrolyte. Potassium nitrate is an electrolyte. Next up, we've got some copper 2 sulfate. Copper 2 sulfate. Put that in here. We'll mix it up to dissolve. And we'll check this one out. We see that it too is an electrolyte. And then the next one, make sure that our water is not conducting. We'll go ahead and add some ethanol to this. And if we go ahead and check this one out, we see that the ethanol is not an electrolyte. So let's go back and review our answers here very quickly. Potassium nitrate, electrolyte. Copper 2 sulfate, electrolyte. And the ethanol would be non-electrolyte. Now, where have you heard the term electrolyte used before? Gatorade. And as I had a student tell me earlier this semester, I guess Gatorade came from Florida Gators. I don't watch football a whole lot, but apparently the Gatorade was created for the football team, and Gatorade was popularized out in sports. And why in the world would we be using the athletes using electrolytes? What if they need? Right, and each time we use electrolytes, the other treat sweat, how much is sweat taste? Salty. And so you might say, okay, well, so we use the electrolytes. Let's go back to the definition of the electrolyte. When you define the electrolyte, it's substitutes that conduct electricity when dissolved in water. So then we go back and have to go, why would we need anything in our bodies that conducts electricity? What is it in our body that conducts electricity? Our brains and our nervous system does, exactly. What else does? Our muscles do, and their heart. I mean, if we want to monitor what's happening to the heart, we take an electrocardiogram. Okay? And so we monitor the electrical activity of the heart to observe what happens. And we do muscle contractions. That involves electrical activity. Impulses that our nerves make within our brain. Those are all based on electrical signals. And so if we sweat those things off then, our body no longer functions properly, and we need to replenish those electrolytes. So then if you think back to Gatorade, and if you ever tasted Gatorade, how does it taste? Okay, well, now imagine if you're replenishing electrolytes, what you would be doing is basically salt water. Okay, but most of us do not take great pleasure in drinking salt water, so you make them more palatable by adding in sugar. And so the sugar then is stuff that provides us with energy. Okay, so when you're taking food, you're taking in energy in the form of sugar and carbohydrates and fats and stuff like that. But that does not help us out when we need to move our muscles and everything. We still have the energy, but that energy doesn't do us any good unless we also have the electrolytes in there to allow those electrical signals to be passed along. Now, the next thing I want to test out here is, any questions on electrolytes yet? Is anybody making a connection? What types of substances are electrolytes? What do we look for? What are we seeing in there? Hydrogen and oxygen? Sure. How would we describe these? There we go. How would we describe something like salt, and potassium nitrate, and copper 2 sulfate? What types of compounds are these? Ionic, exactly. So we see that these ionic compounds are electrolytes. And then we go back to our definition a little further, and we say that these are substances that conduct electricity when dissolved in water. So that takes us to the next substance we're going to look at. The next substance we're going to look at is this stuff here, which is chalk. Anybody know the primary composition of chalk? There's some carbon in there. This is going to be calcium carbonate. Now all of a sudden some people that were in lab yesterday are saying, oh, I remember hearing of calcium carbonate. Where do we use calcium carbonate? Antacids. Exactly. If you ever tasted an antacid or chewed one before, how is it often described as tasting? Chalky. Why? It contains chalk. Because chalk is calcium carbonate. And so it's the same active ingredient that's in there. And if we look at its formula, calcium is Ca with a charge of 2 plus. Carbonate is CO3 with a charge of 2 minus. 2 plus and 2 minus will cancel out, and we get CaCO3. We now want to test to see what happens when we put the calcium carbonate in here. And I think this is the next question on the Socrative app, except I need to demonstrate what happens here when we put the calcium carbonate in water. I'm just going to break off a small piece. And some of you in here, I know, also did the egg lab. Turns out that if you don't have chalk, and you don't have Chems, something else you can use to neutralize your acid in your stomach is eggshell. Primary composition of eggshells is calcium carbonate. And so all you need to do is grind up some eggshells. Yeah, that's all you need to do. Eggshells, calcium carbonate. And how many did that egg lab? Oh, you put it in the vinegar, what happened? Do you remember? All right, I removed the shell. And when you observed it removing the shell, you looked at it, did you notice the bubbles in there? Yeah, there were some bubbles. So just like we see baking soda reacting with vinegar, the same thing is happening when you take eggshells react with vinegar. The bubbles that are forming kind of foamed up. So I put this in here, and now if you look at this chalk, it looks like it's kind of powdery. If it sits for a while, that cloudiness is going to disappear, and that chalk is going to settle at the bottom. So the calcium carbonate is not dissolving. So did I get this next question up here yet? I think so. So the next question here is, Do you think that calcium carbonate, now it's not dissolving, do you think that calcium carbonate is an electrolyte or not? Get the answers locked in. We'll check this out. 5, 4, 3, 2, 1. And we see that calcium carbonate is not an electrolyte. And it's not an electrolyte because it did not dissolve in water. If we go back to our definition, way back up here, our definition of electrolytes is that electrolytes are substances that conduct electricity when dissolved in water. So even if we have an ionic compound, if that ionic compound does not dissolve in water, it will not be an electrolyte. So we say that this one here is a non-electrolyte. If you want to put in parentheses down below, we could just remind ourselves that this is insoluble. It does not dissolve. Okay, next up. First of all, any questions on these? Yeah, go ahead. I have here. Anybody happen to have a sports drink like that? This is true. If your parents told you that you start going blind when you get older and you can't hear, it is very true. I can never find the remote, and I can't hear what you're saying half the time. So they're not lying to you. I'll tell you, they listen too much rock and roll when you're a kid, not good. All right, so we'll check it out. How about that? And what do you think if we tested some tap water? Because remember, I've been taking this here, which is deionized water. If it's deionized, that means we have taken the ions out. So if we check the tap water itself, what should we expect to find here? Probably dim light, because you'll see that we do have a small amount of electrolytes that's contained in here. Okay, so good question, and thanks if you didn't notice that. Whoever did notice it, appreciate it. So thank you. Anybody else? And you know this was in the kit. All right, so next question. Let's go on to these, and this takes us really where we're headed in this chapter. Which of the following substances, and now before you answer, if you want to write out these formulas, let's do that. Which of the following substances would be classified as electrolytes? And we'll select all of the answers that apply. So, looks like we have ammonia. And next on our list was hydrochloric acid. Then we had acetic acid, and then we had sodium hydroxide. Slide these up. And let's write out some formulas for these now. That will help us in our answers. Ammonia. Now, this is one of them that you were supposed to memorize the formula for. Ammonia is NH3. Hydrochloric acid is HCl. Acetic acid from acetate. So that means you have hydrogen combined with C2H3O2, which is the acetate ion. And then we have sodium hydroxide. Sodium is Na with a charge of 1 positive. Hydroxide is OH with a charge of 1 negative. Single positive, single negative, what happens? They cancel. So these are the formulas. So we go back to our Socrative app, and we ask ourselves, which of these substances would we predict are electrolytes? I'm going to get these laid out here while you do that and discuss your answers with a neighbor if you wish. I'm going to try to get these in the order that you will see them. Okay, let's get your answers locked in. And let's go ahead and see how we did. We'll count down. 5, 4, 3, 2, 1. Looks like we're kind of all over the place, but it seems like the most of us believe that sodium hydroxide will be an electrolyte. So we are going to test them in order. We're going to start here with ammonia, which is a formula of NH3. We'll go ahead and place some water into this one. We'll check to make sure that the water does not conduct. And then we'll go ahead and add some ammonia to this. And we will put it back here. How many did say ammonia was going to conduct? Okay. And we'll see that it does. Now, compare this light, though, to a previous one that we said was an electrolyte, like this one. And how does the light compare? Dimmer. So now we are actually going to classify these even further. When the electrolyte is not as bright, we actually refer to that as being a weak electrolyte. So we would say that ammonia here is a weak electrolyte. In all of the previous ones that were electrolytes, we're going to go back and rate these as being strong electrolytes. So every one that we labeled here before as an electrolyte, go back and label it now as being a strong electrolyte. And in the last one we looked at, though, however, the ammonia, we saw that this one is a weak electrolyte. And we'll go down and look at the HCl next. So with the HCl, we'll go ahead and take some water. Make sure that our water by itself does not conduct. We'll add a small amount of HCl to this. And then we check this out, and we see that HCl is strong electrolyte. HCl is a strong electrolyte. And then we'll look at the acetic acid. And for the acetic acid, what I'm going to do with this one is I'm actually going to put some water into one of them, and I'm going to put the acetic acid into the other. We're going to test both of them. Here's the water. Here is the acetic acid. But now what happened with each one of them by themselves? Nothing. But we pour the acetic acid into the water, and we see that it does conduct, which means that acetic acid is a weak electrolyte because we see a dimly lit bulb. So it is a weakly conducting solution. Okay, so weak electrolyte. And then our last one that we're going to look at is sodium hydroxide. And this is the one that the majority agreed to be an electrolyte. And sodium hydroxide is a solid at room temperature. So we'll go ahead and take a small amount of NaOH. Put that in. Get it dissolved. And then we'll check it real quick. And Like the majority predicted, this is an electrolyte. Specifically what type? Strong electrolyte. Now there's something that the last four have in common with each other. And what they have in common with each other is that they can either be classified as acids or bases. So in this group right here, we're either looking at acids or bases. I think we can guess which one are acids. Which ones would they be? Well, the names should even go away. Hydrochloric acid and acetic acid. Furthermore, as we've written them, remember that when we write them, we typically write the hydrogen first. So each of these here are acids, and the ammonia and the sodium hydroxide are classified as bases. And if we take this a step further, when we talk about electrolytes, we said they are substances that conduct electricity when dissolved in water. What this also means is that they must have ions in solution. But they must have ions in solution. And so we come back to these down below here. We said they must have ions in solution. And we said that these are acids and bases down here. If we look at this one, this clearly is not an ionic compound. What that must mean is that something like ammonia will react with water to make ions. Just like we saw when we took the acetic acid. By itself, what happened? Nothing. It didn't conduct. If we took the water by itself, we saw that it didn't conduct. But when we mixed them together, then they did conduct. And what that's telling us is that there must be a reaction that takes place. And there is. And the reaction that takes place is this, and it's one on how we base these definitions. We define an acid as being a substance that produces these ions when dissolved in water. And we define a base as being a substance that produces these ions when dissolved in water. And either an acid or base is dissolved in water, it will conduct electricity. Exactly. That's because acids produce these ions. One of these two ions you should know the name of already. Which one do you know the name of? Top or bottom? Bottom. What do we call this one? Hydroxide. Well, I want to be consistent. Typically we indicate bases with blue. So these here are hydroxide ions. Anybody know the name of the first one? We haven't discussed these before. Well, now we are. These are called hydronium ions. These are called hydronium ions. And the only place you're going to find hydronium ions is in aqueous solutions of acids. Again, hydronium ions are only found in aqueous solution of acids. So aqueous means it must be dissolved into water. So we will not see hydronium ions unless we dissolve an acid into water. And so, if we then look at the different substances, we start with the NH3. NH3 was the first one that we looked at back here. So right here, NH3. We want to show what happens, and we'll do this based on definition. If we put NH3 into water, by definition, if it's a base, it is going to produce which ions? Hydroxide ions. And then we kind of need to do the math to figure out what's left over. If we have an OH over here, the other ion that must be present is going to be NH4 with a charge of 1, not a negative, but positive, because we notice now that these charges must cancel each other out. They must be neutral, just like it's neutral on this side altogether. And of course, now we've named these ions before. These are called ammonium ions. This here is ammonia. This here is the ammonium ion. So when we place this into water, we produce hydroxide ions. Then if we look at the next one, we had hydrochloric acid. So with hydrochloric acid, we want to show what happens. Remember now, HCl we did not classify as a base, but rather we classified as an acid. And if it's an acid, that must mean it reacts with water to produce hydronium ions. And it reacts to produce hydronium ions. As far as what's left over now, this hydrogen gets attached over here to make H3O. What's going to be left behind? Cl with a charge of 1 negative. But it's the hydronium ions that indicate that we've produced an acid. And then if we went on to the next one, we have acetic acid, which we have the formula here for acetic acid. We take acetic acid and place this into water. Each one of them by himself did not conduct electricity, and now it is. So because it's an acid, that must mean it produces hydronium ions. And we ask ourselves, what is left over? Basically, the hydrogen goes over and attaches it onto the water to make hydronium, and then what's going to be left? Remember the name of this ion? Acetate ion, exactly. So that's C2H3O2, and its charge is going to be 1 negative. And of course, now our last one is easy. This one here is sodium hydroxide. This one is basic. This one doesn't even have to react with water. What will happen with the sodium hydroxide, and what makes sodium hydroxide different than the rest of them, sodium hydroxide is an ionic compound to begin with, and because it's ionic to begin with, it simply separates into sodium ions and hydroxide ions. And sometimes we write an H2O above the arrow to indicate that it's not reacting with the water, but simply because it is present in the water, it can separate into ions. So then by definition, we see that this first and last one produce hydroxide ions, which means it is classified as a base. And the second and third one produce hydronium ions, which means it's classified as an acid. Well, then we go a little bit further from here and do this. So I'm going to write these down. We have base, and acid. The next step is going to be to look at whether they were strong or weak electrolytes. And so we saw that the first one was a weak electrolyte. Then we had then it was strong, then weak, then strong. So we come back here. This was weak, then it was strong, then weak, then strong. And then we actually put those terms together. And what we say is this. We say that a base that is a weak electrolyte is classified as a weak base. And an acid that is a strong electrolyte is a strong acid. An acid that is a weak electrolyte is classified as a weak acid, and a base that is a strong electrolyte is a strong base. So when we use these terms, weak and strong, as they apply to acids or bases, has nothing to do with how dilute they are or how concentrated they are. It has to do with how strong or weak they are as electrolytes. And in terms of the reactions, which ones make a lot of ions? Is it the strong ones or the weak ones? Strong ones. So in the strong ones, we have an arrow that stays one direction, like this. So it's one direction. That means they produce a lot of ions. But in the other ones here that are weak, we actually put in a double arrow. So wherever we see the weak electrolytes, we put in a double arrow. And what that double arrow indicates is that this reaction goes both ways. It tells us that there's not any of these ions that are in there for the weaks, which should make sense because when we observe them, how bright is the bulb? Not very bright. That's not very bright. That tells us there's how many ions? Relatively speaking, there is a small amount of ions. So we put those double arrows in there to indicate that they are going to be very small. And so, with this, are there any questions that you have here today? Okay, we got about 2 minutes left here. Just to wrap up with a quick story. Back when I was a student, I think I was probably in my third year of chemistry at the time, so I should have known better. But we were doing a lab in which everything was dissolved in this stuff here, which is the pure acetic acid. If I walked around with this pure acetic acid in here and just kind of weigh it over the bottle, what should happen is I walk that forth here, you guys should start smelling. You starting to smell this? Okay. You're starting to smell the acetic acid that's in here because, again, this is 100%. So, we did a lab when everything was dissolved in this, and it's like, oh, wow, this is kind of cool. Everything in here smells like vinegar. Okay? So, we used it kind of sloppily, if that's the word. That's how we used it. It means we didn't really treat it with a whole lot of care, because after all, glacial or pure acetic acid is a weak acid, just like we observed. So we kind of splashed it all over, we cleaned it up with paper towels and everything. The lab smells very fragrant. And about 3 or 4 days after this lab, we came back to class again, and my colleagues and I were talking to each other, and they were saying, "Can hands feel funny?" Feel kind of funny. And there was some people in there that were starting to get blisters on their hands. And this was before we wore gloves and lab or anything. By about 5 or 6 days, what happened was those small blisters were growing together. And eventually what happened is we had solid blisters that were the entire palms of our hands running out through the fingertips. And learned a very important lesson in all of this. And the lesson is, well, gloves, which we didn't have when there was such thing, but you didn't wear that in lab. I mean, we wore a holy chance as a badge of honor because that meant we had been in the lab. But what I did learn from it is it doesn't matter whether they are strong or weak. As long as it's concentrated, like we said about the properties of acids, is all acids and bases cause skin burns when concentrated. Even the acid that's called vinegar, if it's pure, will cause those severe burns. So, anyhow, learn from me. That's it. See you next class. Study session today at 10 o'clock down in the Academic Support Center.